Okay, folks, welcome to the next lecture. In this lecture, we'll be taking a look at differentiation by rule. So first of all, differentiation has loads of different names. So differentiation is just one part of calculus. It's probably the part that secondary school students are most familiar with, but differentiation in itself has loads of different names and there's loads of different terms, but the methods are always the same. So it could be called finding the derivative, dy dx, differentiation, and then this one is a bit unusual. This is called f dash x. So it's f with a dash and then x. And this is if we're using our function notation. Remember, if a function is described by fx, then its derivative is described by f dash x, and if we need to differentiate again, as we'll see in later lectures, it's called f double dash x. Still the same thing. Could be called the rate of change. This is why we're particularly interested in it as scientists. We're always interested in the rate of change. The slope of a tangent to a curve is a little bit more of a formal way of saying the rate of change, or just the slope. The slope of a curve is another way of saying we need to differentiate in order to find this slope of a curve. And the slope of a curve is the rate of change. So don't be put off. In the following lectures, I'll be using all these different terms to try and get you familiar with the terminology, but the maths is always the exact same. And now we're going to take a look at the rules of differentiation. Now, all of these rules could be derived from first principles, and there is a video on first principles on Moodle. I won't cover it or I won't examine it, but you can take a look at it if you want. Some of you might have met it in secondary school. It's quite laborious and tedious, so the rules bypass all the kind of tedium. So I'm going to try and explain each rule in terms of slopes as we go along. So, just as I was saying, differentiation from first principles is pretty cumbersome and tedious, and our rules are used to speed up. So the first rule, if we have a simple function that's just a constant, there's no x terms involved, then the derivative is 0. dy dx is 0. And if we take a look, say if we have a line y is equal to 5, that's what it looks like. It's a horizontal line passing through y is equal to 5. Similarly, y is equal to 3 would pass through there. Y is equal to minus 2 would pass horizontally through there. But the thing is with these is, I hope you'll see, is that regardless of where you are on that line, the slope is 0. A horizontal line has a slope of 0, and that's all we're saying here. So it doesn't matter what value a is. Like I said, it could be 5, could be 3, could be minus 2. The slope of that line is always 0. So that's all the first rule is telling us. Any constant term, when we get the derivative of it, the derivative is 0. Rule 2, this is our linear equation. Y is equal to ax. So remember, we used to call am when we were looking at linear functions. So the value in front of x is always the slope. So when we get the derivative of y is equal to ax, dy dx is just equal to a, the slope, because that's what we're looking for. So here we have an example, y is equal to 4x, and this is what the line looks like. Now, what this is telling us, the derivative, is regardless of where we go on this straight line, the slope is always going to be 4. Doesn't matter what point we pick. So any point on that line, the slope is always 4. Similarly, if we had a slope of y is equal to 1x, which would look like this, regardless of where we go on this line, say y is equal to 1x, that's what I'm drawing here, everywhere on that line, the slope dy dx is equal to 1. I usually use red as well to denote the derivative or the slope. So you'll see this throughout the following lectures. Like the function is generally written in black and the derivative is generally written in red. Another way to look at it, what I often say is, the black equation tells us where we are. This gives us the position. So when x is equal to 1, y is equal to 4. When x is equal to 1, y is equal to 4. So the black line tells us where we are at any point, or the black equation tells us where we are. The red function tells us the slope at that point. Third rule. This for scientists is probably our most important rule, because if you remember, this semester, or we've recently been looking at linear functions, quadratic functions, cubic functions. We also looked at reciprocal functions. So each of these is determined by the value on n. So for us as scientists, this is a particularly important derivative rule or differentiation rule. And the derivative looks like this. So what happens is the power comes down and is multiplied, and then we add -1 to the old power. So say if we have, say, y is equal to x to the power of 5, my derivative the power comes down, the 5 comes down, and then we add -1 to the old power. So that then becomes 4. So it's very important that the wording as well. I don't say reduce the power by 1. I always say add -1 to the old power, because it's just if we have a function y is equal to x to the power of -3, often people would make the simple mistake of thinking, oh, I reduce the power by 1, which gives me -2, but that's not. You're actually increase the power by 1. So this is why I always say add -1 to the old power, and then you're much less likely to make that simple mistake. So now, for scientists, sorry, I should be clear, this is probably the most used rule in differentiation for scientists and for engineers in general. Multiply the function by the power and add -1 to the old power. So we'll take a look at some examples of this one now. Here we have y is equal to x squared, so dy dx. Bring down the power, and then add -1 to the old power, and we get y is equal to 2x. I've just thrown up a few pictures of the functions as well to remind you what they look like. Here's our cubic function. It's a simple cubic, so it looks like this. And now when we get the derivative, dy dx, bring down the power. The x obviously stays, and then we add -1 to the old power. Now, don't be put off by these ones. First of all, what we have to do here is change the form. So it's difficult to do it like this, but if you remember from our power rules, when a power is below the line, we can bring it up and change the sign. So I haven't done any differentiation now. I'm just changing the appearance of the function we're given. So I hope you'll agree that these functions are equal. They're both reciprocal functions. Now when we get the derivative, dy dx, bring down the power, the -1 comes down, the x stays where it is, and now we add -1 to the old power, and this is what our function looks like. And just to be polite then, guys, in general, if the function is written in this format, like this, we should write our derivative in the same format, using fractions, so to speak. So this is just -1. That's going to sit up on top. Remember then, a negative power can be written below the line. So I hope you remember those from your power rules from semester 1. So you might need to revise those if you don't. So like I said, first step, change the format of our function so that it's written as a power. And then bring down the power, add -1 to the old power. And then, like I said, it's good manners to rewrite it in the format in which the function was given. Now both of these are correct. Mathematically, they're both the same. And this is just, again, this is what that curve looks like, typical reciprocal curve. Just what I have here in red, the red line is actually giving us the slope. So the blue line tells us where we are, like I said. The blue line gives us the black equation, where we are at any moment. And the red line here is actually telling us the slope. So just to kind of make sense, but these do not intersect. They're just giving us more information. Here we would see the slope is negative, and it's actually, when x is 1, the slope is -1, etc. So the red line is just telling us about the slopes, but that diagram might be a little bit confusing, so I'll just move on. Now, here's a question for you guys to try. So it's just based on that rule 3. Find the derivative of the following functions. Here's our rule. And just have a go at each of these. Part D might confuse you a little bit, but remember, sorry, I'll just write that in black. Remember square root as a power. So once we write it as a power, now the rule comes into effect. Bring down the power, add -1 to the old power to get your derivative. So I'll let you guys have a go at them. Now we'll take a look at rule 4. Y is equal to sine x, and this is our typical sine curve. Remember, it starts here. Now if I try and draw a graph of what's happening with the slopes, I hope you forgive me, just it takes a little bit of explanation. Now here, when x is 0, that's a 45-degree line passing through, so the slope is actually 1. Here, at 90 degrees, the slope is 0. Here, the slope is 0 again. Sorry, I should go to here first. Here, the slope is -1. Here, the slope is 0. Here, the slope is +1 again. Here, the slope is 0. The slope at that point is -1. So when I actually start to join the dots, what I'm actually getting is, if you recognize this from the trigonometry lectures, it's the cosine curve. So the derivative of y is equal to sine x is cos x. And rule 5 then, we look at the cosine curve, again with the same logic. I'll quickly try and sketch it in. Here the slope is 0 when x is 0. So remember, horizontal line, all of these points here are going to have a slope of 0. So there'll be 0, there'll be 0, that'll be 0, this one will be 0. But here now, at this point, when x is actually equal to 90 degrees, the slope is minus 1 because it's downhill. Now here, the slope is plus 1 because it's going uphill. Here the slope is downhill. Here the slope is uphill. And hopefully again when you see it, now again forgive my poor dot joining skills. Now it looks like a sine curve, but it starts at 0 and heads downwards. So it's actually minus sine x, that red function. So the slope of the cos curve, the blue line, the slope of the cos curve is described by minus sine x. So that's the derivative. So there's a much neater version of my poor scroll. And I hope you'll agree that a red line there, that describes the slopes of the blue line above it. dy dx is minus sine x. So all of these rules, guys, are given in the log tables. You don't have to remember them. You know, in college, I don't believe in learning stuff off by heart. So all of these rules will be available to you in any exam situation. So now we'll take a look at rule 6. So that's our exponential function, y is equal to e to the power of x. Now this is the easiest derivative to remember because the derivative of y is equal to e to the power of x is e to the power of x. So I'll try and explain that now. So here we have our exponential curve. So this blue line is y is equal to e to the power of x, typical exponential growth curve. And if we pick a point, we let x equal to minus 1. So if we use our calculator, y is equal to e to the power of minus 1. When you get your calculator, you'll get 0.368. So this point here is described by minus 1 for our x value, and our y value is 0.368. What the red function here is telling us is that at that point, the slope of the line is also 0.368. Now if we take a look, we let x equal to 1. So again, black is just telling us where we are. Y is equal to e to the power of 1. And when you get your calculator, that's 2.718. So here we have the point. There's x, there's y. And at this point, the slope of the function is 2.718. So the exponential function is the only function whose derivative is itself. So in other words, the output, the y value, is the same as the slope. Now the last function is our log function, in this case the natural log function. Y is equal to the natural log of x. That's what the natural log function looks like. And the derivative of this function is 1 over x. So remember, this is our reciprocal function. And now this graph again looks a little bit confusing. These lines don't cross. We simply have our blue line, and the red line is telling us the slope at any value. So when x is equal to 1, y is equal to 0. So if we let x equal to 1, the natural log of 1 is 0. What the red line is telling us is the slope at that line is actually plus 1. So really we can see what the blue line and the red line is telling us. On the left, the blue line, the slope is very, very steep, and then it's getting less and less and less. And that's what the red line is describing us. The slope is very steep and positive. All the values are positive. But then as x gets bigger and bigger, the slope is decreasing. So I hope those graphs aren't confusing. You often see them in textbooks about derivatives, so I said I'd include a few here just to try and give you an idea. But it's very important to realize is the red line is kind of superimposed. These lines don't cross in a kind of a simultaneous equations kind of way. It's just the red line is telling us what the slope of the blue line is at any moment. Whoops, sorry, wrong button. So that guys kind of sums up all the basic rules of derivatives. And like I said, you'd always be given these in an exam situation. They'd usually be in your log tables. Now we're just going to take a look at two more kind of general rules that apply to these. The first of these is the constant rule. And it's very simple. It simply means, and it applies to any of the rules, is if there's a constant in front of your term, so say if we have y is equal to 3x squared, so 3 is our constant, or say y is equal to 0.32, we'll just say e to the power of x actually, just to keep something simple. So in each of these we have a constant, and then we have our function in x, which I'm just drawing a bracket around. The derivative of this, the constant term stays where it is. And then we differentiate the function in x. So for this function, dy dx would be, so the constant stays, and now I'm going to differentiate this bit. Remember, f dash x means dy dx, so the power comes down, and we add minus 1 to the old power. So in this case, dy dx would be, numbers do what numbers do, and we get 6x. Similarly, in the next function, so the constant stays where it is. And now we differentiate this bit, and remember the derivative of e to the power of x is itself. So it looks like nothing's happened, but that's just the way it is with derivatives. With the exponential function, it's the only function whose derivative is itself. I'm just thinking of another one, say y is equal to 2 sine x dy dx. Well, the 2 stays, and then we differentiate sine x, and if you remember from rule 4, I believe, the derivative of sine x is cos x. So I think it's really kind of, I really like differentiation. I think it's amazingly powerful. It's so simple to get from here to here. But this red equation tells us so much about this function here. We now know the rate of change at any moment for this curve. So say we have y is equal to 3x squared. Now we know this is a quadratic. It's going to look something like that. This equation, for any x value, we feed in. Our equation here will tell us the y value, and that's what allows us to draw that black curve. But the derivative, dy dx, like I said, the 3 stays by 2x. So the derivative, just like I did, is 6x. Now for any x value, we can tell the slope when x is minus 1. Here, we now can tell the slope at that point. Put minus 1 in for x, the slope there is minus 6. Similarly, the slope when x is 1 is plus 6. For 2, when x is 2, the slope is going to be 12. So we can tell the rate of change of our black function very easily. So I think calculus is kind of one of the most powerful forms of maths. I personally really like it. I know a lot of students don't tend to like it, but it's so simple, but yet so powerful. Anyway, I'll stop raving on about it. I'm sure that you'll have had enough at this stage. We take a look at the last rule then, guys. So simply put, the derivative of any constant value multiplied by a function. So simply the constant stays. I spent a bit of time trying to word that, and it still looks a bit verbose. The constant stays, and then you differentiate the function in x bit. If an expression is to be differentiated, it consists of several terms. So here we could have, say, sorry, just get my pen. Y is equal to 2x squared. We'll just say 2x to the power of 4 plus 8x. All this rule says, so there's u and there's v. The summation rule simply says is we differentiate each bit separately. So in this case, dy dx, the power comes down, 4 comes down, multiplied by 2 gives us 8. Reduce the power by 1 or add minus 1 to the whole power. So that's the first one differentiated. And then when we differentiate 8x, this was rule 2, that'll simply become 8. So that's what this rule is saying, is if there's lots of parts, lots of terms, remember a term is separated by a plus, minus, or an equal sign, then we simply differentiate each term independent of each other. So now we'll just take a look at a couple of examples. Find the derivative of the following functions. So here, there's a couple of things going on here. We have our constant rule. We also have our summation rule. There's 3 terms. But we just differentiate each term separately. So I'm just differentiating the x squared. The 3 stays. Now 8. Now this is just rule 1. So when we differentiate minus 8x, it just goes to minus 8. That's rule 2. And then any constant value, the plus 2. Remember, this was rule 1 here. Any constant value just goes to 0. So you can write in plus 0, but it's usually trivial. So in this case, our answer becomes 6x minus 8. Here's one now. Again, we'll be using, so dy dx. For the x cubed, we use this rule. Again, we use rule 3 for this bit. Now, the 2 stays, but then when we try and differentiate the x squared bit, the power comes down. So we have the 2 multiplied by 2 gives us 4x. Add minus 1 to the old power and it's x to the minus 1, which we would leave out. Minus any sign stays. Now we're using rule 3. Minus 3x just goes to minus 3. And the constant term is using rule 1. So once you get used to it, guys, it can be very quick to find your derivative. And this red equation gives us the slope of the black equation for any value of x. This one's a little bit trickier. So we just need to, anytime you have powers below the line, it always makes sense. Notice I'm not changing the function. This becomes 2x to the power of minus 2 plus 2x to the power of minus 1. So I always prefer to write rational terms or reciprocal terms using powers first. And now I can differentiate dy dx. So the power comes down, gets multiplied by the constant, so minus 2 by 2 is minus 4. Now add minus 1 to the old power. So this will become minus 3. So that's the first term differentiated. Again, the power comes down. Minus 1 by 2 gives me minus 2. And then add minus 1 to the power. Now, like I said, it's good manners to write it back in the old form. So this will be minus 4 over x cubed. And then minus 2 over x squared. This one is fairly straightforward. I don't need to adjust it. dy dx. The derivative of cos x is minus sin x. Now the 3 stays there. And then the derivative of sin x is just cos x. So like I said, once you get used to them, it can be a very quick process. And just a couple more. Now, this one's a little bit trickier, but nothing we haven't encountered. Sorry, I'll just rewrite it first in black, because I can see the rational term here. So this would be y is equal to 2 times the natural log of x minus 3 and then x to the power of minus 1. So now when I get my derivative, dy dx, so the 2 stays. The derivative of natural log is just 1 over x. The minus 3 stays. Again, I'll just do it a little bit more laboriously. I think I might have gone through some of the other ones a bit faster. So the minus 3 stays. Now, using rule 3, I bring down the power. I keep my x, and I add minus 1 to the old power. So when we tidy this up, top by top, bottom by bottom, this gives me 2 over x. Now minus 3 by minus 1 is plus 3. I'll just write it as a plus. Now it's 3, and then x to the power of minus 2, remember, we can write like that. So that's my answer. And again, for any x value now, I can just feed into the red equation and my answer will give me the slope. So if I want to know what's the slope of this function at x is equal to 1, I go to here, do my maths, and now I can just let x equal to 1 and the slope will actually be 5. So it's very powerful. Like, we don't have to draw any graphs, we don't have to draw any dodgy tangents like that. Every student, if they've done it correctly, will all arrive at exactly the same answer. And now this one again looks a bit tricky, but there's nothing really untoward here. Again, we'll just write everything. So 0.2 e to the power of x plus 0.3. Our power is below the line, so we write it using negative powers. Now we can differentiate dy dx. The constant stays, the 0.2 stays. When we differentiate e to the power of x, the derivative is itself. Here, the constant stays, 0.3. But now I'm differentiating this using rule 3. Bring down the power. Keep my x. Add minus 1 to the old power. And then I'll just write it out neatly. Minus by a minus, minus by a plus gives me a minus. Numbers do what numbers do. And then x to the power of 4. And that's my answer. So I hope you can see kind of, once you know what you're doing, like it's very straightforward to arrive at this derivative. But remember all the time, guys, that red equation allows me find the slope for any value of x. And as scientists, we always see the slope as the rate of change. Now you can imagine trying to draw this curve would be very laborious, and then trying to draw a tangent to that curve at any point would also be very laborious and also probably a bit inaccurate. So now we just some problems for you to try. Have a go at each of these. Remember, if the value is below the line, bring it up, change the sign, and then differentiate, just like I did in those previous examples. So have a go at each of those, and I've kind of covered, I think, the examples I did previously should show you how to do these ones. So now we're just going to do the same thing, but just the question has changed very slightly. Find the slope of the tangent. Y is equal to 3x squared minus 8 at x is equal to 2. So we just simply get our derivative. Remember, dy dx. In this case, the 3 stays. We differentiate x squared. So dy dx is equal to 6x. And now we're just interested in what's the slope at x is equal to 2. We feed 2 in to our red function, our slope function. So now we know the slope of the tangent to this quadratic at x is equal to 2 is equal to 12. Now just visually, there's our quadratic smiley curve we're interested in at x is equal to 2. And we've now determined the slope at that point is 12. But we didn't have to draw a graph. I'm just including the graph to give you a visual idea of what we're actually doing. Find the slope of this tangent. So when we work this out, remember, dy dx. This will be x to the power, sorry, I'll do that in black. is equal to 0.2 e to the power of x plus x to the power of minus 3. Now when we differentiate, we've done this bit before, and here power comes down, add minus 1 to the old power. And now we're interested in at x is equal to 2, so we just feed in 2 for both of these values. And obviously it's a calculator exercise from there. And there's our answer. Now if we were to draw a graph visually, that's what the curve looks like. You can see it's quite unusual. And we're interested in what's the slope here. And we've just worked that out that it's 1.29 after a bit of rounding, obviously. We could go to 10 decimal places if that was required. When you're drawing a tangent with the graph, there's no way you could get the slope accurate to 10 decimal places. Not unless you were a master artist and you were doing it on a huge sheet of paper. So I hope you kind of see the value of calculus. Like, it's very powerful. It gives us these slopes of very complex functions. We can determine the slope in a matter of minutes. One more. So, sorry, I'll do our derivatives first. dy dx. So again, I'll just lay them out. So the constants stay. And now I'm using rule 3. The power comes down. Add minus 1 to my old power. The power comes down. Add minus 1 to my old power. This will give me 6x squared plus 8x. And now we're interested in when x is equal to minus 1. Feed minus 1 in for x. And we get dy dx is minus 2. So we now know the slope of the tangent to this function at x is equal to minus 1 is minus 2. And again, if we were to draw it, it's a cubic function. This is a cubic function. It's a polynomial, so it's got several turning points. And we're interested in what's the slope when x is equal to minus 1 at this point here. So the slope there is minus 2. So now just some questions for you guys to try, very similar. Find the slope of this tangent at x is equal to 1. So there's a visual representation of what we're looking at. The next question. Sorry, again, you'll have to pause each one. I'm going a bit quick. Find the slope of this tangent when x is equal to 90 degrees, because it's a trigonometric curve. So again, visually, that's what we're looking for. Where is the slope there when x is equal to 90? And last one then, a little bit more complex. That's what it looks like. And we're interested in what's the slope when x is equal to 1. So now, that finishes off this lecture. I hope it makes sense. I hope you kind of appreciate some of the reasons why I like differentiation. Just, it's once you get used to using the rules, it can be a very powerful way of analyzing functions at a much deeper level than just the baseline equation gives us. So just the black equation gives us a simple, this just allows us to draw the graph. But when we differentiate it, and it literally takes a matter of moments if I don't mess everything up. This red equation just opens up all new levels of analysis. We can now determine how quickly the slope is changing at any moment, whether the slope is positive, whether the slope is negative, anything like that. So I'll stop yapping, guys. Thanks very much for your patience, and we shall chat to you again shortly.